Hello, and welcome to Lecture 4. This is our fourth lecture in our discussion of electricity and magnetism, which means we're starting to dig into more ideas that are interconnected to the ideas and variables we've established so far. So far, we've talked about charge, we've talked about electric field, and we've talked about voltage. Okay? Now we're going to add something else, capacitance. Okay? And capacitors, which are the actual physical devices that allow for capacitance in terms of practical application. Okay, so let's think about our objectives. We want to become familiar with the physical quantity capacitance and its relation to other electrostatic quantities. Okay, like, well, you guessed it, right? Charge, electric field, and volts, they're all going to come up, all right? Then we're going to understand the ways of expressing the energy stored in a capacitor, so energy, okay, and the work done to separate charges across the gap of a parallel plate capacitor. Finally, understand how capacitors lined up in different arrangements, series and parallel, the terms we give to them, I'll specify what that means, create sums of capacitance that follow from conservation of electrical energy, okay? So we're definitely talking about energy, but we should expect that. Are we going to be talking about forces here? Actually, very little. That said, we've talked about the forces within a uniform electric field before, right? We did that very early on when we defined Coulomb's law. Where do uniform electric fields come from? I've said it a few times, but I'll forgive you for forgetting, certainly. They come from capacitors. Capacitors are the poster child, so to speak. They're the way we get uniform electric fields. So that's certainly important. And the reason we continue to introduce these new electromagnetic, in this point, electrical quantities is because we have to establish these building blocks. We have to have the main players in terms of ultimately circuits. That's where we're going. We're not there yet. And in fact, this is the first, well, the capacitor is our first so-called circuit element. Okay. Now there's gonna be more. So that's interesting. It means we're turning a page. We're getting to a new way of dealing with this information. Okay. All right, so we certainly want to establish the key terms here. There's a lot to unpack. So first of all, what is capacitance? Okay, all right. Well, it is charge storage ability of a certain arrangement of conductors. Okay, that's the general idea. Because of course, conductors allow for the free flow of electrons, charge in general, but certainly electrons for metals. And then so we have that conductor. We can then build up charge somewhere, and then that can store the charge. That's what capacitance is about. It's the ability to store charge. Okay, it's like a storage capacity. Okay, the similarity to the word capacity is not a accident, right? It absolutely is about capacity, storage capacity. All right. It is defined as charge per voltage, and the unit is known as the farad. The farad is the coulomb per volt, and it has dimensions of inverse mass, length to the negative second power, so that's 1 over L squared, time to the negative fourth power, and current squared. These are the fundamental dimensions, which would also be the base units, which would be kilograms, meters to the negative 2, kilograms to the negative 1, seconds to the negative 4, and amps squared. Okay, and of course we could replace the amps with coulombs per second. Okay, okay, so that's the basic idea of what we're talking about with capacitance. All right, so with that in mind, we want to get on to thinking maybe just for a moment about how it's a little bit more of a abstract idea perhaps than we've looked at so far. And now I made the argument that electric fields are an abstract idea. They require us to sort of visualize things. But it was also very arguably basic because we took force and we normalized by charge. We made a map out of it, which was abstract, but we normalized. The same thing with volts. We took potential energy and we just normalized by charge. But capacitance is wholly unique. It's not just about normalizing by something, just dividing by charge. It's a new way we need to think about storage. We'll see that it's related to energy most directly. Okay? All right, and for a parallel plate capacitor, the capacitance is entirely dependent on the area and the separation of the plates, which is the perfect segue to what I want to talk about, of course, which is parallel plate capacitors. Now, why do I make this step? Why do I go from the general definition to this what sounds pretty specific, parallel plate capacitor, because really this is what we talk about. Anytime we talk about a capacitor, it's a parallel plate capacitor. Anytime we care about capacitance, it's because of parallel plate capacitors. So there really is only one case that we look at, okay? All right, well, where's that arrow going? To the following picture. This is it. I feel like this is a good basic expression of a parallel plate capacitor. It's connected to a battery. We'll talk a lot more about batteries later. Turn out they're another circuit element. But here's the idea, right? These are big metal plates, right? They allow for the free flow of charge, right? They have some cross-sectional area and a distance between them, right? That's the basic idea of a capacitor. And opposite sign charges build up on the opposite plates, okay? Okay. So two metal plates that are manufactured to not touch. That's the idea. There has to be a gap between them, okay? So a capacitor is known as a circuit element, okay? That's something we'll get into much later, or much more in later lectures, so don't worry about too much for now. And they function when connected to a voltage source like a battery, okay? So we want to actually, think about in practicality, they're always going to be connected to a voltage source. Again, that term voltage source is a little bit new, but we've seen voltage. The idea is where we've created some potential, right? We've done some work to separate charge. That's what batteries do. They're actually turning chemical energy into electromagnetic energy to separate the charge, right? Because after all, voltage is just potential energy normalized by charge, right? But the point is you need a voltage source to really think about what capacitors are doing, okay? And batteries are the best way. Of course, you can connect it to a wall. The problem there, though, is that walls are alternating current, and that's a discussion for another day. Okay, so a capacitor is represented by the symbol 2 parallel bars. Okay, so we show that there's like a wire coming in and a wire going out. Okay, wire in, wire out, and then that's the actual capacitor symbol. All right, the variable is the letter C. Okay, now if you think about it, then what's the letter for the units? F. So let's take a minute there, right? So the unit is the farad, okay? And we'll see that come up, right, in our final answers if we're solving for capacitance, okay? And it is the coulomb per volt. But here C is a unit and it's a coulomb. But here C is a variable and it's a capacitor, okay? And also it's capacitance, all right? So first of all, let's appreciate that here it represents the physical device, the capacitor, right? If we're using it symbolically in the equations that I'm introducing in the next page, it would represent capacitance, okay? But furthermore, we have to be really careful that we know that this is a variable and this is a unit, right? Because they're both uppercase C. Now I tend to put my units in parentheses, but sometimes when I'm solving a problem, I don't. So you want to make sure you're not confused by that. You have to make sure that you know the difference based on the context of the problems and knowing the equations when we're talking about the variable capacitance and when we're talking about the unit, I almost said the coulomb, but when we're talking about the unit of the, what is the coulomb? Yeah, coulomb for charge, okay? Yeah, it is, absolutely, it's measuring coulombs, okay? This is the unit of charge, okay? Okay, all right, now that's just gonna take practice, no way around it. Now, there's a big idea. There's two ideas that we have to think about when we think about capacitors, and that's how you combine them together. Because you can either put them in an arrangement called putting them in parallel, or you can put them in series. Now, you may have seen something like this when you looked at springs. It's okay if you haven't, but that would be the only time you would have seen it in the mechanics class. Because if you put springs and you kind of line springs up one after another, that'd be springs in series. On the other hand, if you line up springs side by side, that's springs in parallel. And that creates very different forces that the overall arrangement of springs exert on, say, like a hanging weight at the bottom of those springs. And so that there's actually a really good analogy there between how these things function, okay? But point being, that's the only time you may have seen it. So this idea of parallel and series may be entirely new. So I'm going to kind of break down how to describe them. Parallel just means stacked, okay? So stacked capacitors have an equivalent capacitance equal to the sum of individual capacitors, okay? So I actually changed just the word capacitors and individual capacitors, okay? Because it's the device, not the quantity, okay? So stacked capacitors have an equivalent capacitance, because that is the quantity, equal to the sum of individual capacitors, okay? I'll go ahead and correct that in the upload, okay? All right, so this is what it looks like. It's simple, just arithmetic. You just add them together. So the equivalent capacitance, which might as well be called total capacitance, but equivalent is the most common way to express it, is just the sum of C1 plus C2 plus C3. but we need a picture, don't we? Okay, so this is it. This is what I mean by stacked. I'll zoom in a tad here. So, because you're stacking them up, right? C3 is on top of C2 is on top of C1. These are three stacked capacitors. Now, we never say stacked. We say these are three capacitors in parallel, okay? All right, I'll come back to that idea in just a minute. Okay, you can tell maybe what they look like. Okay, so in order to prove that this is the equivalent capacitance of these three, in this case, three parallel capacitors, let's consider a couple things we already know. Okay, the total charge on these capacitors is the sum of the charge on capacitor 1 plus the sum of the charge on capacitor 2 plus the sum of charge on capacitor 3. Because after all, Q are charge. All right, here we're using uppercase Q to represent the charge on an individual capacitor. Okay, all right, that makes sense, right? Because electrons are building up on all these capacitors. There's more capacitors, there's more space for electrons to build up. Okay, great. And all the capacitors experience the same voltage. Okay, well, that's because the voltage is across. It's a physical, right? Physical separation. Think about equal potential lines. All these capacitors must experience that same voltage difference on whatever electric field exists due to the wire. Okay, all right. So from the definition of capacitance, okay, and I'll come back to that in our key equations on the next page. But this is the definition of capacitance as charge over volts, but of course that is completely consistent with the definition here. Charge storage ability of certain arrangements defined as charge per voltage. That is the definition, okay? Okay, that means that then we could say, okay, then the total charge is then just going to be capacitance 1 times voltage, capacitance 2 times voltage, and capacitance 3 times voltage. Okay, the total charge on all of these capacitors. Thus, the equivalent capacitance of all three of them is just the total charge divided by the voltage. But after all, there's only one voltage. So look what happens. The voltage just cancels out. So then what we get is what we were looking to prove in the derivation, that the equivalent capacitance of these three capacitors in parallel is just the sum of the three. Okay, but what happens if you put them in series? And what does it even mean to put them in series? Well, let's see. Okay, so in series means lined up capacitors have an equivalent capacitance that is less than any one capacitor. Notice there I use the correct word, capacitor, as I should have and will correct up here, right? So lined up capacitors have an equivalent capacitance that is less than any one capacitor. Now it turns out it has a particular mathematical relationship of how much less it is, but I think that's a good way to start. So the idea there is if you line up capacitors, you're actually making a weaker total capacitor. Why is that? Well, let's think. Okay, here's the picture of what lined up capacitors look like. Yeah, they look like they're lined up, right? That's called in series. So in this case, there are three capacitors in series, C1, C2, and C3. Okay? So now let's derive that fact that the total or the equivalent capacitance of these three lined up capacitors is indeed less than the capacitance of any one of them. All right? So the total voltage across the line of capacitors is the sum of the voltages across any individual capacitor. So here, when they're lined up like this, when they're in series, they don't share a voltage, not at all, right? Because the electric field is continuing. Instead, there's a proportional voltage across each of them, okay? But the total voltage is the sum of the three. Just as before, the total stored charge was the sum of the three. But what about charge? Well, from the principle of induction, consider lecture 1, right? Review lecture 1 if you need to. We know that the charge on each of them must be the same, okay? All right, because it's an inductive charge on each consecutive plate. Okay, again, because they're not physically touching, are they, right? There's gaps, okay? So from the definition of a capacitor as being charge divided by voltage, we can go ahead and substitute in for our shared Q and our total voltage, and our expression becomes like this. Then consider that each voltage is proportional to whatever the capacitance of the individual capacitor is. So for example, V1 becomes Q over C1, but it's the same Q, so all the Q's cancel, just as all the V's canceled before, and we're left with this expression. So the equivalent capacitance is the reciprocal of the sum of the reciprocals, which is a mouthful. But if you actually plug in numbers, imagine like this is like, 1 over 1/2 plus 1/3 plus 1/4. Do that in your calculator. You're going to get a number smaller than a fourth. It will always be smaller than the smallest value, okay? All right? Well, in that case, you get a number smaller than 4, smaller than 2, because 2 is the smallest value of capacitance measured in farads, okay? So you'll get some number that is, I think it's gonna be like 1.5 or something. It'll be some number smaller than 2, okay? Because it will always be smaller than the smallest capacitance, okay? And this is exactly how you calculate it. Cool. All right, last idea, last key term, dielectric. What is a dielectric? Okay, so a dielectric is a thing, but it's also a way to increase capacitance. I think that's the first idea you should stick in your mind. It's just dielectrics are all about increasing capacitance. Because up to this point, what's been in this gap? Well, a perfect vacuum, honestly. It's been something that is just doesn't allow for the flow of charge, right? Charge can build up, I'll zoom in on this, charge can build up on this plate, maybe negative charge, inducing a positive charge here, which then by conduction causes another negative charge to build up, which then induces another positive charge, and so on, okay? But in between the gap is a vacuum, total perfect insulator. But here's the thing, it actually is better, and it's counterintuitive, but amazing. It's better, instead of putting a perfect vacuum between your capacitor plates, to instead put an insulator, but an insulator that is composed of molecules of which can become dipoles. So what I mean is the molecules themselves can become dipoles, okay? So let's look at that, okay? Here's the picture, kind of come back to it in just a moment. Okay, so an insulator that is placed between the plates of a parallel plate capacitor. That's the definition of a dielectric. Okay, this increases the capacitance. That's why you do it, by the dielectric value of the material K. Okay, now don't confuse this with K as the constant, the electrostatic constant. There, the subscript is Ke. Right, this is just K. Okay, it is a dimensionless quantity. It is material specific, so you look it up in a table. Right, some engineering table being like, what's the dielectric constant of, sodium? What's the dielectric constant of silicate? What's the dielectric constant of glass, of water, and so on. Okay. Now, a dielectric functions, right? Just kind of quick overview here, by creating a secondary opposing electric field, the polarization field, which attracts more charge to the plates than the external voltage would otherwise allow. Okay, now, because the idea is that so far we've defined capacitance as charge per voltage, but where does capacitance come from, right? Well, capacitance it's dependent on the voltage, certainly, right? So the way really you can think about it is you can often, in terms of the actual independent variable, it's going to be Q, the amount of charge you can get, is capacitance, something you built, manufactured to hold a certain amount of charge, times voltage. So that means you can only get so much charge for a certain voltage, okay? So really, its charge is dependent on voltage, and then C is dependent on something else I'll talk about in just a minute. Capacitance is dependent on other quantities, okay? It turns out the actual physical parameters of the capacitor, okay? But in reality, Q, the amount of charge you store in capacitors, is dependent on the external voltage. And you're just kind of stuck there. You can only get so much charge for a particular voltage, okay? You can up your voltage and get more charge, but maybe you don't want to, okay? If you're thinking of the actual application of these capacitors. Well, in that case, you put a dielectric in between your parallel plates, and now you can get more charge per volt, okay? Because what's happened is the external electric field, the one in blue here, has polarized all the molecules in the dielectric. What then happens is the dielectric then creates a magnetic field. Yeah, I said magnetic, I don't know why. It creates an electric field that goes in the opposite direction. This is zooming in on one of these dipoles, right? The electric field of this individual dipole right here, what's going to go from positive to negative, so it goes in this direction. So that means that there is this polarization electric field that is opposing the external electric field, the original electric field, the one that comes from the external voltage source. Well, you might think, well, that's bad, right? I don't want to oppose the thing that's driving my capacitor in the first place. But here you actually do. Because by creating this opposing polarization field, you allow for more charge to build up. Just one of these amazing intricacies, just amazing details of the subject of electricity. Okay, all right. So let's get into our key formulas. All right, so the first one is no surprise. This is going to be the definition of capacitance, okay? All right, and we'll start with a graph, okay? I feel like so far we've been covering the concepts. Let's look at this quantitative graph here. This is charge as a function of voltage, okay? And here it's delta V, right? But here it's just the voltage gap across the plates of the parallel plate capacitor, like in the figure on the last page, right? Because that's what we're talking about here, parallel plate capacitors, okay? Now graphs are great, right? Because they tell us the relationship, right? Here we have our dependent variable, our independent variable, okay? What is the slope? The slope is the capacitance. All right, so it's the proportionality between charge and external voltage. All right, and clearly it is. It's rise over run. It's the slope. Well, in just a minute, we'll talk about the meaning of the area under that curve, okay? But it's linear, which is nice, mathematically speaking. Okay, so capacitance, measured in units of farads, which is the coulomb per volt. Well, a volt is a joule per coulomb, so that means another way to express a farad is a coulomb squared per joule. Okay, charge squared per energy. Great. Okay, Q is just the charge on either plate. It's not the net charge, it's just the charge, so like as was in the picture, we've got positive Q and Q. So the magnitude charge on either plate is Q, okay? And then, then delta V is the voltage across the capacitor. It's the voltage gap. That distance D in the figure, that's where the voltage gap exists physically, okay? All right, so here, I mentioned this, I hinted at this, here's how we actually calculate capacitance. You might be like, well, hold on, this is how you calculate capacitance right there. There's the formula, it's charge over voltage. That's fine if you know the charge and you know the voltage, but in practical means, if you want to start from scratch, you got to build a capacitor. To build a capacitor, you have a certain cross-sectional area and a certain distance between the plates. That actually sets the capacitance. Then, once you set the capacitance, then you're going to find out how much charge you can store based on how much voltage you supply. So again, really, in some textbooks actually presented this way, it almost makes more sense to rewrite this fundamental equation as Q equals CV, okay? Which is because that's really the way you're going to use it a lot of time. You're going to solve for the stored charge in your capacitor, practically speaking. The reason we don't is because this is the definition of capacitance. So it is a natural place to start. Okay, so here, epsilon naught, we saw this in lecture 1, okay, because the electrostatic constant is 1 over 4 pi epsilon naught, okay? But there we just use the electrostatic constant. But here we're not. Instead, we're going to use that more fundamental quantity, the permittivity constant, and it's 8.85 times 10 to the negative 12 farads per meter. And if you want to see another way to express it in different units, refer to lecture 1. And actually, I really support that idea, because if you're getting stuck with all these new quantities, go back to the units, spend some time, express things in different units, just run through them, break them down to the basic fundamental units, like I do with the dimensions. Okay? Then C is just the capacitance of the capacitor. Okay? Then we have the electric field. I'll get back to that. D is the distance between the plates. Okay, so that's the same D there. Okay? And then A is the cross-sectional area of the plates. Okay? So you can also think of it as the area, the surface area of either plate. You gotta make sure you don't double count it and say, oh, it's the total surface area. It's not. It's either the cross-sectional area of the arrangement or the area of one single plate. Just like Q is the charge on one single plate. Okay? All right. So I said I'd get back to electric field, and that's because here I'm saying that this is how we determine capacitance, how we actually find capacitance based on area and distance between the plates. Again, how we build a capacitor. But the reason it works is things we've already seen in the previous 3 lectures. Because after all, electric field is defined as voltage over distance, right? Absolutely, it is. I mean, the first time we saw it, it was force per coulomb, right? The units of the electric field were newtons per coulomb. But more recently, we've seen the units of the electric field as volts per meter, right? Which is a totally valid way of thinking about it, because the electric field crosses all those equal potential lines, okay? It's the streamlines on the topographic map, okay? So it's volts per distance. In the meantime, electric field is also the charge divided by the area, okay? So essentially, the electric field encloses a certain charge. The electric field that goes through that area has to be equal to charge over the area. It's the flux of the electric field. It's electric field that's actually flowing out of a certain area. In this case, the cross-sectional area between the plates. Okay, so that has to be the case. All right? All right. And don't worry about that if you're not completely comfortable with that derivation. This does come from Gauss's law, but again, give it the attention that it needs, which is not that much. All right. So let's then take a look at this. Okay, what's this? Well, first of all, this is the Greek letter sigma, but what does it represent? It represents charge over area. Okay, it's Q over A, right? Well, it's the charge density. Okay, so it's the area charge density because it's charge per area. Okay, but it's simply that. It's just coulombs per square meter in terms of the units. Okay, charge density. That makes sense? Like, it's like you could think if you wanted, you could even express this as like number of electrons per square meter, right? In that case, you would just want the charge per electron. So that's basically what we're getting at here. Okay. Now the energy bit. Okay, I said energy would be important. Well, let's show why it is. Okay, so this right here is the work, W for work, to charge a capacitor. Okay, and it's the shaded area, all right? And the shaded area has, well, the shape of a triangle, which means geometrically speaking, a triangle is 1/2 base times height. Well, in this case, the base is voltage and the height is Q. So it's 1/2 QV, okay? Well, that's exactly what we see. That's the work to charge the capacitor, which also is, right, conceptually speaking, also the stored energy in the capacitor. Because if you do work to charge the capacitor, then the capacitor has stored energy, okay? That's what capacitors are good for. They're good for storing energy, okay? So it's just 1/2 QV based on the area under the curve in our linear relationship between charge and voltage, okay? Now we can do a substitution and express it in terms of the quantity capacitance instead of the charge, and then we can even express it in terms of capacitance and charge independent of voltage. So we have here is 3 ways to express the energy stored in the capacitor depending on what your known values are, just for convenience, okay? But you see then that they're very interconnected, okay? All these formulas all related to capacitance are very interconnected. You know 2 things, you know 5 of the quantities, right? Because they're so connected. All right, so one of our last unique equations here, we have the mu sub e, okay? This is the Greek letter mu, okay? Mu, all right? This one, by the way, was sigma, okay? All right, but here we have mu. What is that? Well, that is the volumetric charge density, okay? So it's the actual charge density in terms of energy between the plates. Because after all, that energy has to exist somewhere, and it exists as the electric field between the plates. That's where the energy actually exists, between the plates, okay? That's that, because it's all these electrons that want to fall, right? But they're not able to fall because they can't cross that gap of a perfect insulator, okay? That's the energy. That's where the energy exists. So the charge per volume between the plates is mu E, and it's just the stored energy of the plates divided by the volume between the plates. See how this is the volume between the plates? Because if you think of the plate as having an area A, and then this is D here, well then what happens, 3D speaking, is we end up with this rectangular solid, all right? And that's what this is. That's a volume, see? Because it's square meters times meters. It's a volume, okay? So it's energy per volume, all right? And then we can actually rewrite this, okay? I don't show the derivation here, but we can just go ahead and substitute in the appropriate expression for stored potential energy of the capacitor, okay? Potential energy, right? And then it simplifies to this, which is pretty neat, because then we can see that the stored energy of the capacitor is dependent entirely on the electric field strength, okay? But of course, the electric field strength itself is dependent on the voltage, okay? All right. So here we have the dielectric, okay? This is kind of a similar figure to the one I had on the previous page, showing the dipoles that exist in the insulator that create that opposing electric field, all right? But here's the actual equation. Here is the capacitance that we saw above, that is without a dielectric, and here's the capacitance with the dielectric. There's the dielectric value, the dimensionless value K. And it's just some value. You look it up, it's like dielectric of 5, dielectric of 1.2, dielectric of 20, right? Just a number, okay? And it's empirically determined. They've done experiments with these materials and found out how good they are at creating these opposing fields and thus increasing the effective capacitance of the capacitor. Okay, so that's it. All right, and here's a cool idea though, is because the total electric field, because the electric field is going to be flowing in this direction, but then there's the opposing electric field. So the effective electric field, which is the total, is the original external electric field, the one that's driven by the voltage of the battery, right? Minus the electric field of the polarization. The electric field of polarization being due to the particular dipoles that develop in the material. And that's why different materials create different dielectrics, because some are better and some are worse at creating these dipoles based on how the molecules function. All right, and so then that then is equal to the charge density divided by the dielectric value times the permittivity. Okay. And so with a dielectric, the effective field strength is reduced by a factor of 1 over the dielectric constant, okay? So again, it's a reduction of electric field that actually allows for better storage ability. Beautifully counterintuitive, okay? All right, so there, one more thing to label, the dielectric constant itself, okay? All right, last 2 equations, these are just reproduced from the key terms on the previous page, capacitors in parallel, right, lined up, and then, or sorry, not lined up, stacked up, and then capacitors in series with a lined up, okay? And then I included pictures just for reference. There's the parallel case, all right? And then here, in this case, what's equal is the voltage, and what sums is the charge. And then in the series case, shown here, what is equal are the charges, and what sums is the voltage. Just a reminder of, the fundamental difference between having capacitors in these two different arrangements. And it's not always three, right? But this is just a good example, right? Kind of a nice way point where it doesn't just apply to two, it applies to any number, as is shown here by the dot, 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 but three is a good way to derive it. Okay, all right, I think we're ready for some practice. All right, so our practice problems, we've got 5 types. Type 1, simple problems that involve relating capacitance, voltage, stored charge, electric field strength, separation distance, plate cross-sectional area, and charge density. Okay, fair enough. Now you might be like, well, that's a lot, right? But really, these are such simple equations. These are really, really simple relationships, okay? Type 2, problems that involve relating stored energy of a capacitor to capacitance, voltage, stored charge, and volumetric charge density. So see the difference? Here, type 1 is all about capacitance. Type 2 is about the energy, okay? Kind of different focus between the two. Type 3, problems that involve capacitance or energy of a capacitor includes a dielectric. Okay, so if a dielectric is involved, let's consider that separately, so it's its own type of problem. Type 4, problems of varying difficulty that involve finding the equivalent capacitance of an arrangement of capacitors in parallel and series. So there we're going to use those formulas of having capacitors stacked up or lined up. Okay, and finally, type 5, fairly complex problems that involve the calculation of individual capacitors that are part of an arrangement of capacitors. All right, so you'll see what I mean by that. Basically, type 5 is really using the definitions of voltage and inductive charge that we saw in the derivations of the formulas for capacitors in parallel and series. That's what really type 5 is about. It's about going back to those derivations, but using them to solve a problem. Okay. All right, example 1. A parallel plate capacitor has a capacitance of 25 microfarads. What potential difference across the plates is required to store 7.2 times 10 to the negative 4 coulombs, all right, on this capacitor? So this is how much actual charge we're storing on the capacitor, okay? All right, notice this is not C for capacitance, this is C for coulombs, okay? Good. All right, so we want a voltage difference. We want the voltage across the plate. We know the capacitance of the capacitor and we know how much charge it has, okay. So in that case, we're just simply gonna use the definition of the capacitor, but solve for V, and it's as simple as that, okay? This 10 to the 2 here is I just canceled out my scientific notation since a micro is 10 to the negative 6, and here for the actual amount of charge, I had a 10 to the negative 4. Well, if I take 10 to the negative 4 and I divide by 10 to the negative 6, well, division of exponents is like subtraction, so I have negative 4 minus negative 6, which just equals positive 2. So then effectively my order of magnitude is 10 squared. And then I get my 29 volts. It looks good. All right, you can also just put this in the calculator. All right, then in part B, if the gap between the plates is 1.04 millimeters, then what is the electric field strength within the capacitor? Well, now that I know the voltage, I can easily use this extra information of the gap distance to easily find the electric field, because the electric field, after all, is just volts per meter. Okay, and that's because the electric field is uniform, right? It doesn't get like stronger when you get closer to one plate. That's a fundamental assumption here that never varies with capacitors. The electric field is always uniform inside the capacitor. Good. All right, so it's just 29 volts divided by the separation distance. Here I've converted it to meters, of course, and there we go. 2.8 times 10 to the 4 volts per meter. In other words, 28,000 volts per meter. Wonderful. Okay, example 2. A parallel plate capacitor has a plate area of 0.2 square meters, a fifth of a square meter, and a plate separation of 0.1 millimeters. To obtain an electric field of 2 million volts per meter between the plates, okay, the magnitude of the charge on each plate should be what? So the idea here is we have a desirable electric field strength, and we need to know how much charge is going to be on each plate, okay? So let's think about how we work that out. Okay, so we know that the charge is dependent on the cross-sectional area and the gap, okay? Well, I'm sorry, the capacitance. The capacitance is determined by the cross-sectional area and the gap, and just some constant of the universe called the permittivity constant, okay? We'll actually come back to that when we talk about the speed of light. Pretty cool. All right, so then the capacitance, by definition, is Q over V, okay? V, by definition, is electric field times distance, right? Okay, make sure you got that. So then I can just set the two things equal to each other, all right? So I'm just setting this side of the equation, left side of the equation, equal to this right side of the equation, equal to the right side of the equation, right? Eliminated the capacitance, since I don't care about it, all right? And then D naturally cancels out, the separation distance cancels out. So then I can just go ahead and solve for the charge. So then we see that the charge is dependent on the electric field strength, a constant, and the area. Wonderful, okay? So really, that's the whole idea. Plug in my numbers, right? And I get 3.54 microcoulombs. That's how much charge I would need. That's also just how much charge would naturally happen if I ran this particular electric field, because by running this particular electric field, I'd be effectively externally setting the voltage, right? It's the strength of the battery I've connected to the capacitor, okay? All right, so then in part B, what is the charge density of the plates? Okay, I just want to make sure we use all the formulas. Right? It's pretty straightforward. All right, so then sigma is charge density, which is just charge per area. Well, I know the charge and I know the area, right? I already, I found the charge in the part A, so that's easy. And then I know the area, we're given it. So there we have it. We have the charge density, 1.8 times 10 to the negative 5 coulombs per square meter. Okay, so basically it's about 200 thousandths of a coulomb per square meter. Okay, that's useful. All right, now we can also express this, interestingly, as just electric field times permittivity times A divided by A, because after all, this is charge. We saw that in part A. All right, so then if I cancel out the cross-sectional area, I get a really neat result. I get that the charge density is dependent on the electric field alone. So if you know the charge density, well, the other way around, most likely, if you know the electric field, you know the charge density. But that actually shouldn't be a surprise because the volumetric charge density was also determined entirely by the electric field strength. Well, so is the area charge density. Pretty cool, right? All right. And that of course, will just give us the same number. I just wanted to show it worked. Okay. All right, and so finally in part C, what is the voltage difference between the plates? Okay, well, voltage by definition is just electric field times distance, at least for uniform fields. And so then we just take our electric field multiplied by our distance. Notice this is the first time we've actually used distance. We were given it to begin with, but it would have been superfluous, in other words, useless information, if we hadn't been asked for the voltage as we were asked for part C. And it turns out to be 200 volts. So this is connected to a 200 volt battery, big battery. Okay, all right, so let's move on to our next well, I just didn't say example, but I have a couple of concept questions. All right, so we've got concept question 1 and 2. All right, so these are great ones to make sure we're going back and understanding some of the basic ideas, right? Because I laid it all out in the key terms, but that's a lot of upfront information. Let's test this, right? So a really good idea with these concept questions is see if you can come up with answers, even if you don't feel confident about them, before you hear me do it. Okay, because that's a good way, like kind of just put yourself out there, try to think about what your best guess is, and then at least you'll have some assumption that's going to be challenged. Okay, potentially. All right, so question 1. A capacitor has a charge Q, right? There's some charge on the plate. The plates are then pulled apart so the distance between them is larger, right? Some external work, maybe like physically someone put on insulating gloves and pulled the capacitors apart. After that, after they are pulled apart, what happens to, I should say they, okay, what happens to the charge on the plates, the electric field between the plates, and the voltage between the plates? Okay, so pause if you need to, and come up with what you think the idea is, okay? All right, so idea is there's an initial separation distance, d naught, and we make it bigger, right? They're further apart, okay? Pull them apart. Okay, so the charge remains the same. It's unchanged, okay? Why is that? Why is the charge unchanged? Because it has nowhere to go, right? These are completely insulated. There's no wire, right? They're cut off from the outside world. Someone charged these plates up and then just left them completely insulated, right? And so then if you pull them apart, it's got to be the same charge. You can't just get charged from nowhere, okay? Can't get charged from a vacuum, okay? Well, what about the electric field? It also remains the same, right? Because if the charge isn't changing, then the electric field can't change either, okay? Because what ends up happening is there's an exact balance between the effect on the voltage and the effect on the distance. They exactly balance out. So the electric field remains unchanged, okay? Now, what happens to the voltage? Well, the voltage does increase because if the distance got bigger and the field didn't, then the voltage went up, okay? So that's the one thing that did change. That makes sense because you had to do work to pull these plates apart. Because after all, there's a bunch of positive charges on one side, negative charges on the other. That's the idea of a capacitor, right? Well, if you have these charges that want to be next to each other and you pull them further apart, you had to put energy into the system. And if you put energy into the system, it had to go somewhere, right? And so it went into the fact that there's now a greater amount of energy per charge, okay? So if we'd asked for, if there was part D and I asked for how much potential energy is there stored in the plates, that would have also gone up, okay? Make sense? All right. Okay, so question 2, what's the difference here? Okay, so same thing, we're gonna start with a certain distance, we're gonna pull them apart, okay? But the difference here is now they're connected to a battery, which means that now the voltage remains constant. The only thing that changed before. Now we're forcing it to remain constant. Okay, so the capacitor has a charge Q and is attached to a battery. The plates are then pulled apart so the distance between them is larger. You're still doing work on them. After that, after they are pulled apart, what happens to the charge on the plates, the electric field between the plates, and the voltage between the plates? So all the same questions, but I already gave away C. Okay? All right, so here's the idea. Here's the voltage, right? Here's the battery, positive N and negative N. Okay? All right. So the charge Q decreases. There's actually less charge per plate now. All right, because think about what's happened. You've increased the distance, right? Which means that since the area hasn't changed, the capacitance has gone down. The ability to store charge has actually got worse. Okay, you want plates to be as close together as possible, then you can store more charge. And if the capacitance has gone down and the voltage has remained the same, then the only thing else that can decrease is the charge itself. So effectively, there was a bunch of electrons, on this side, right? Because they were up or over this side, on the bottom side. There are a bunch of electrons that are pushed away from the negative terminal of the battery, negative into the battery. But then when you pull them further apart, the battery, it's still pushing electrons, but its push doesn't matter as much. So some of these electrons will redistribute themselves into the wire itself, right? So they'll all be as far apart as possible because their individual electrons want to repel each other. So they're gonna like spread out as far away from each other as possible. But when the plates aren't as close together, it doesn't make sense to have them as packed together on the plate. So some of them will spread back into the wire. So essentially there'll be a back current into the wire and into the battery itself. Okay, kind of cool. All right. Okay. And part B, what happens to the electric field? It also decreases. The electric field decreases, okay? Now this isn't the desirable type of decrease that happens when you put in a dielectric. This is a decrease for a different reason. And it's so easy, but try not to confuse the two, okay? Because here we have an electric field decreasing and the actual charge decreasing, okay? Whereas if you keep the distance constant and introduce a dielectric, then there isn't a decrease in electric field, but rather an increase in charge. But the key difference is when you added the dielectric, you didn't change the separation distance. And after all, right, that's so important to the capacitance. Okay, all right, but in this case, no dielectric, just larger gap between them, the electric field decreases, all right? And finally, the voltage, as I said, remains unchanged by definition, because that's the whole thing. There's a battery. The battery supplies a constant voltage. That's what batteries do. Okay, they are a voltage source. Okay, so let's move on to our next type of problem, example 3, one that involves energy. A capacitor charged to 1.5 volts stores 2 millijoules of energy. If the capacitor is charged to 3 volts, it will store how much energy? Let's see. Okay, so here we have the one of our 3 ways to express stored potential energy in a capacitor. All right, and so then we can simply solve for Q. This is the right one to choose based on the information we're given. So we're going to solve for C. I think I said Q, but solve for C, the capacitance. Okay. And so 2 times the potential energy divided by the voltage squared. Okay, there's our potential energy, there's our voltage, making sure to square it. And there we have the capacitance, 1.78 times 10 to the negative 3 farads. So 1.78 millifarads. Okay, so then the potential energy, we needed that to actually ask the question, because then it says if the capacitor is charged to 3 volts, then how much energy is stored. Okay, well now we increase to 3 volts. We're going to take the capacitance, okay, and then find our new stored energy, 8 millijoules. So we went from storing 2 millijoules to 8 millijoules when we doubled the voltage. Think about the proportionality there. Doubling the voltage, and did we also double the energy? No, we quadrupled it, because there's a squared relationship. You double the voltage, you get 4 times as much energy. Pretty cool. Okay. All right, another one of energy. A parallel plate capacitor is designed to contain a volumetric charge density between its plates of 13.9 joules per square meter, okay? Energy per volume, with a plate area of 0.41 square meters. I know that I tend to use a lot of big areas. In reality, that's because when people actually make capacitors, they roll them up on these really tightly wound rolls, like a tiny jelly roll. And so the idea there is you actually have a lot of area because it's all rolled up. Okay, so if this capacitor is connected to a 12-volt battery, then what must be the plate separation distance? Okay, so let's think about this, right? So how do we connect these? Because it seems to be some disjointed quantities, right? Because we know this relationship, right? We're given a formula, but it didn't involve D. So how do we tie them together? Well, we go back to the definitions and use some algebra. Okay, so here is a good starting point for the definition of stored energy in a capacitor. Okay, well, energy per volume, right? So it's potential energy per volume, right? Because after all, cross-sectional area times gap distance is volume. Okay, notice I'm not using the one with there's 1/2 epsilon naught times E squared. Absolutely, you can. There's no dead end here. You just have to do more algebra in that case. Okay, So then we're going to use this expression for the stored potential energy, one that's dependent on capacitance and voltage. Makes sense to use one that has voltage after all, because we're given the voltage. And then, since we're asked for distance, we better use a formula that relates capacitance to distance, right? So these all kind of make sense, right? I think just think about naturally choosing the formulas that have at least some of the known values, and then think about the unknown you're looking for, which is distance, okay? So then we can then do a substitution, and we get this. Maybe like, hold on, where did this come from? All of a sudden, I rewrote the energy per volume equation as the following. Well, let me show you. Okay, so the idea is that this is the same AD, right? Since it's in the denominator, I just multiplied by 1 over. Okay, and then this right here is C. Okay, so this expression is C by not the definition of capacitance, but the way we actually calculate it based on its physical parameters. Okay, see where that came from? Because after all, potential energy is just this whole expression. See, that's where the 1/2 CV squared came from. See it? Because this is the same V squared, right? The one that's in the potential energy. Okay, so it's multiple substitutions. So I wanted the color coding for you. Okay, A cancels out. All right, so then we just go ahead and solve for D. I just cross multiplied and then isolated the D. It'll be D squared because there's two of them. So essentially I just combine these two D's and then multiply both sides by D squared and divided both sides by mu sub E, which I accidentally wrote as mu sub naught. That should be mu sub E. Mu sub naught is a different quantity, so that's probably why. Easy mistake. Okay, but it's not one we're using here. Technically, we're talking about mu sub E. All right, so anyway, so here is our value. Once I plug in all of our knowns, because the things we knew, right, was the constant, epsilon naught, we knew the voltage, and we knew the stored energy per volume. Wonderful, okay? So there we have it. And we came up with a new formula, right? It's 2 micrometers, which is really close, but absolutely, manufacturable. That's like, nanotech, right? So they're 2 micrometers apart, not even quite nano, because there is a micrometer, which is that's what this is, also known as a micron, is 1,000 nanometers. Okay. Deep breath. All right, let's continue on. Example 5. A defibrillator unit contains a 150 microfarad capacitor that is charged to 2,000 volts. The capacitor plates are separated by a 0.01 millimeter thick dielectric with a constant of 300. Yep, that's right. We're talking about dielectrics now. What is the total area of the capacitor plates? Okay, so let's think about what we know. So we're going to use the definition of well, again, I always call it the definition, really, because it's the one that is usually used when you're trying to find capacitance. But again, it's the manufacturer's equation for capacitance based in this case on the cross-sectional area, the gap distance, and the thing that's between the gap. All right. And so then we're just going to go ahead and solve for A, right? Because we know all the other quantities in this formula, right? So it's very much a plug and chug type problem. All right, plug in the capacitance, plug in the the gap distance, 10 to the negative 5. All right, well, 1 times 10 to the negative 5. 300 for our, let's see, that's our dielectric, of course. And there we have our constant, our permittivity constant. All right, so there we have 0.56 square meters, right? About half square meter. Okay, and then in part B, what is the energy density stored in the electric field when the capacitor is charged? Okay, so here we're going to use this formula, just like in the previous example. All right, and then we'll plug in what we know. All right, and we already know the capacitance, we know the voltage, which we hadn't used yet, and now that we know the area, we're all set to go. All right, and we end up with 5.3 times 10 to the 7 joules per cubic meter. So 53 million joules per cubic meter. It's a lot of energy, right? But these are actually realistic values, right? But of course, that's how these things are able to jumpstart a human heart, because they have a lot of stored energy, all right, per cubic meter. Okay, another dielectric problem, example 6. A parallel plate capacitor with a plate area of 2 square meters and a plate separation of 3 millimeters is connected to a 35-volt battery as shown. Determine the charge on the capacitor, the electric field, the capacitance, and the energy stored in the capacitor. All right, and then with the capacitor still connected to the battery, a slab of plastic with dielectric strength 3.2, so rather weak, is placed between the plates of the capacitor. So the gap is completely filled with the dielectric, as shown. What are the new values of charge, electric field, capacitance, and the energy stored in the capacitor? So what's good about these examples, we really kind of show how all these things are related and how they all change when you introduce a dielectric. Okay? All right, so I'll run through this, because this is a lot of values, short calculations. Okay, these are our known quantities. All right, so we're going to go ahead and find the capacitance. We plug and chug because we already know A and D. So there's our capacitance in farads. It's nanofarads because it's times 10 to the negative 9. Okay, that's a billionth of a farad. All right, and then we continue on to find the stored charge, and we get 2.1 times 10 to the negative 7 coulombs. And then we can calculate the field strength, and we get about 12,000 volts per square meter. All right, and again, we know all these values, right? Okay. And then finally, the stored energy in the capacitor ends up just being 7.2 times 10 to the negative 6 joules, because here it's total energy rather than energy per cubic meter, right? Because it's a rather small scale, right? So the total energy is small because it is physically so small, okay? And then in B, let's introduce the dielectric. How will that change things? Well, first of all, the way it's going to change the capacitance is simply you take the dielectric capacitance is the original capacitance times the dielectric constant. It's simply just C equals K times C. All right, so it goes up, right? Goes up by a factor of 3.2. All right, the stored charge also goes up by a factor of 3.2. That makes sense. That's what dielectrics do. They allow for more charge to be stored. Okay, and the electric field is unchanged. Okay, all right, and then the stored energy is increased. Okay, you know, because this is a bigger number, right? Because it's a smaller fraction. Okay, we went from 7.2 millionths to 2.3 100 thousandths. Okay, all right, so I kind of made a funny voice when I talked about the electric field, because you might be like, wait, the electric field is unchanged? Wasn't the whole idea of the dielectric is it produces an opposing polarization field? Yes, yes, but that's the effective field that's affected, right, by the polarization field. The actual external field is totally independent. It's just the voltage. The voltage hasn't changed, okay? But I do want to take note of that. So I added a couple of lines of a calculation here. So if we can actually calculate the polarization, the actual strength of the electric field that's created by the little dipoles that show up in the material, the actual physical material we put between the plates. And that's just going to be the unchanged electric field minus the charge density times the dielectric times the permittivity constant, and it ends up being 10,800 volts per meter. So it's actually pretty close. So that means that the new effective field is really reduced. The new effective field is only 1,200 volts per meter. So we've actually dramatically decreased the effective field, but the original external driving field is unchanged. Okay, so that's that. We're asking for different things. Now I could ask you for both. That's why I wanted to make sure that you knew the difference. Okay. All right. So finally, some of these problems that involve capacitors in parallel and in series. Okay. Now these are really good. There's really no way to do these except with doing a lot of practice. You got to work through these. Okay. So, but I'm gonna kind of show you some techniques that I take. But I think the approach you take is very much on you. How do you solve them? These are, a lot of things in physics you say, oh, this word problem is a puzzle, right? But these aren't even really word problems, right? You look at them, they really are just a puzzle. You don't have to do much interpretation of the information. You just go straight into the problem solving technique. Okay, so here, find the equivalent capacitance of this arrangement of capacitors. In this case, we have these two capacitors. They are parallel to each other. And then we have this third capacitor that is in series to this arrangement in parallel. See that? Okay, all right. So this is the combined formula. Where the heck did I get this from? Well, these two ones that are parallel, I simply add up their capacitance arithmetically. It's just one plus the other, right? So that means that this expression here in parentheses represents the equivalent capacitance that could replace this 10 and 2.5 in parallel, all right? So it just becomes 12.5. So that means effectively we have a 12.5 capacitor, 12.5 microfarad capacitor, in series with a 0.3 microfarad capacitor. See? And that's all this is. This is the series part. You take the sum of the reciprocals, and then you take the reciprocal of that. And that gives you your final equivalent capacitance. This is the capacitor, or the capacitance of the capacitor, that could replace these three. Because I could just do away with them and just replace them with one single capacitor, as long as it had a strength of 0.29 microfarads. And see how it's smaller than either value, the 12.5, which is the effective combination, and the 0.3, indeed it is. It ends up being really close to the 0.3 because there's such a big gap between 0.3 and 12.5 that always pulls it closer. But it's going to be smaller than either of the two that are in series. And you might be like, wait, but there's three of them. No, because I've already replaced it, right, in my mind. I've already replaced this, and this is a 12.5. See? Because that's the first very simple step. Got it? Okay. All right. Let's do a bigger one. Okay. So find the equivalent capacitance across the voltage source for this arrangement. There's a whole bunch of them. Okay. So you work backwards. You work from the furthest capacitors out towards the voltage source. Okay. So first of all, I would replace these three that are all in series like this. Okay. So essentially, I could get rid of all three of these, replace them with a single equivalent capacitor, which I call equivalent capacitor 1, and it would be 2 microfarads in strength, which, note, is weaker than any of them, right? Okay, ends up being exactly a third because they're all equal to each other. Okay, that's the idea. All right, notice the formula I use, the same formula you'd always use for capacitors in series. Okay, well then, now I have one over here, equivalent capacitor 1, well, equivalent capacitor 1 is in parallel with this original 4 microfarad capacitor. How do you know they're in parallel? Well, because the difference between parallel and series is whether there's a junction between them. So having this new replacement pink capacitor over here, and then considering the original 4 microfarad, they're in parallel to each other because there's a junction between them. If there's not a junction between them, like this, then they're in series. That's the way you always know, okay? So then, since these two are in parallel, I can use the much simpler formula, take equivalent 1 plus 4, and I get 6. And that becomes equivalent 2. So now I've replaced all 4 of these with equivalent. See how I'm doing this? I'm just working backwards, okay? And now I'm going to take these 3, all right? And it's just 3 because 4 is gone now, right? So I'm going to take the 6, the equivalent 2, and the other 6, and replace them, okay? That's what I have here, and I get another 2. Okay, so equivalent 3 is equal to 2 microfarads. Now I've replaced 1, 2, 3, 4, 5, 6 capacitors with a single capacitor. Okay, all right, rinse and repeat. Now we're going to do it again. These two are in parallel, so it's simple addition. We get a 6. And then finally, we've got these last 3, these ones here, okay, these last 3 that are in series with each other. So we use the series formula, and we get back to 2. See, this one is so interesting because they're all 6s and 4s. So it just ends up kind of rocking back and forth. But we get 2 microfarads as our final equivalent capacitance for this entire arrangement. Pretty neat, right? Okay, so we're going to do it one last time, all right? This time, I'm also going to kind of work my way backwards, but I'm going to start on the inside and work outside, right? Because the natural thing to do is replace, say, like this 6 and the 12 and this 2 and 2 with an equivalent capacitor because they're in series with each other. These are pairs of capacitors in series, and then kind of continue to work out from these inner corners, okay? So that's what I'll do. I'll consider these 2 equivalent capacitances, all right? And since they're in series, I use the series formula for summing 2. All right, so equivalent capacitor 2, which is this one up here, is 4. Equivalent capacitor 1 is 1. Wonderful. All right, and then I'm going to consider these equivalent capacitors, again, in a set, right? Because it's like there's symmetry across these corners. All right, now I'm going to have 2 things in parallel because equivalent capacitor 1 and this 1 are in parallel. Why? There's a junction in between. Okay, equivalent capacitor 2 and this 4 over here, they're in parallel. Again, because there's a junction. Okay, well, here's a junction. All right, so then I have equivalent capacitor 3 using the equation for summing up capacitors in parallel, equivalent capacitor 4. All right, so that means the 3, this one over here, is equal to 2 microfarads, and then the 8 microfarads is this one up in the upper corner, okay? All right, and then I'm gonna have equivalent capacitor 5. Okay, well, what's that, okay? Well, that one is going to be the in series of equivalent capacitor 3 and 8. Well, why is that? Well, look, these 2 are in series. Absolutely, right? There's no junction in between them. All right, cool. So that's 1.6 microfarads, okay? And then I'm gonna do the same thing for equivalent capacitor 6, shown right here, because I'm just gonna take the 2 and the 4, and then they're going to be in series. And you'll be like, wait, aren't all 4 of these in series? Well, no, because look, there's 2 junctions in between, okay? And that junction really matters because you've got another capacitor over here. So you can't ignore that junction. The 2, 4, 3, and 8, right? They're not in series with each other. That's why we had to separately do equivalent 5 and equivalent 6, as we've shown here, okay? And they end up being identical values, which is pretty cool because they don't look like they're going to be the same, right? But it ends up being a clever combination of values to get you the same, okay? All right, and now the question here was different. I'll reread it. So for the given arrangement, we're actually finding C in order to have a total equivalent. So because in the last 2, we just found the equivalent. But in this case, we're given a desirable equivalent, and this is our kind of our adjustable thing that we can add in. So the idea is we're going to set C to get an equivalent of 3, okay? So what does that look like? Well, we know we're going to have one last case where we're going to take equivalent capacitor 7, okay? And equivalent capacitor 7 is just going to be C in parallel with equivalent capacitors 5 and 6, okay? So you see, all right? So, or I guess we can really say that equivalent capacitor 7 is equal to replacing 5 and 6, which are parallel to each other, okay? All right? And something you're like, you might still be thinking about it. Really, are they parallel? Well, think about it. Here's our C, right? And then essentially this is what the circuit looks like if you just redrew it, okay? Where this is equivalent capacitor 5 right there, and equivalent capacitor 6 is down here, okay? All right, so in that case, we set it up like this. Our unknown is C, so I simply solve for C. This is a fun equation to solve for your unknown. And here, the idea is that I just replaced equivalent capacitor, the final equivalent capacitor, as 3, because after all, this is the real final equivalent, the replacement, okay? And there it is. C then is equal to 48 microfarads. Okay, make sure you can do this. There's a lot of algebra, right? But this is about as complex as equivalent capacitor problems get. All right, very last problem, very last example, example 10. Two capacitors with a capacitance of 2 and 3.6 microfarads are connected in series. The system is connected to a 40-volt battery. All right, what charge accumulates on the 2 microfarad capacitor? So essentially, we're combining some of the ideas of the key equations to relate capacitance to energy and voltage and electric field and so forth, and combining those with the rules of adding them in parallel and series and so on. In this case, it's a really simple setup. It's just 2 capacitors in series, okay? So when in series, Q is shared by both capacitors. So then the equivalent capacitance is this, which is 1.3, okay? And thus, we can relate the equivalent capacitance to the shared charge over the voltage difference, okay? And we know the voltage difference to be 40 batteries to be a 40-volt battery. So then the charge on this particular capacitor is just 5.1 times 10 to the negative 5 coulombs. All right, wonderful. Okay. And then B, if the same 2 capacitors are connected in parallel, what charge accumulates on the 2 microfarad capacitor? Okay, well, when parallel, each capacitor has the same delta V, the same voltage gap, but they have different amounts of charge. Therefore, the charge is going to be C times delta V, where we use the particular capacitance of the 2, all right, and then multiply by the 40 volts to get a charge of 8 times 10 to the negative 5. So there's actually more charge when they're in parallel than when they're in series, okay? Now that makes sense because in series, they're both operating less effectively when they're in series. Sometimes you want that. Sometimes you want your capacitors to work less effectively, essentially, right? And notice here, we didn't use the particular capacitance of the 2 microfarad. We just used the equivalent, right? Although, of course, we used it to calculate the equivalent. So look at these 2 different approaches, right? This is, again, a really simple case of just 2 capacitors, either in series or in parallel. But it's the same idea that you would do anytime you'd want to say, ask a particular question, like how much energy is stored on this 1 microfarad, okay? All right. All right, so of course you got some more practice problems you can do, and we'll leave it there. I hope this has been a very interesting and in-depth lecture about capacitance and capacitors. Thank you so much for watching.